This is a AM/FM kit, AM/FM radio kit that I put together some years ago. It's made by Alenco. It's, let's get in here, see if it'll focus. It's called the AM/FM 108K. Very nice little unit because not only does it work well as a radio, but it's laid out deliberately to make it easy to demonstrate the radio function to people who are learning radio. And I would like to use it as a demonstration tool to go into the subject of signal tracing. Now, signal tracing is pretty ancient. It goes back at least into the 20s when people would build small crystal detectors with a headphone that they would use to troubleshoot radios of the day. Later, audio amplifiers were added, made the signal strong enough to drive a loudspeaker. And this is sort of the culmination of signal tracers. This is a signal tracer that I bought probably 20 years ago. It is completely solid state. It has a number of features. So let me focus on the front panel, talk about those features, and then we'll try to use it on this radio to show how you do signal tracing. Basically, this consists of an audio amplifier and a crystal detector. The audio amplifier, the gain is controlled by the attenuator that you see here. It's a step attenuator. It attenuates in 20 dB steps. And then a volume control that allows you to vary. When you turn the power on, you see you get an LED. When you turn on a second function called the injector, you get another LED. So let's talk about those two functions. The tracer function, as I indicated, uses these two to control the volume. And the input is through this jack at this point. The output of the amplifier comes out through the jack above, and you have a selector switch that will allow you to select either the speaker, the meter alone, both of them, or the internal speaker or an external speaker. And you can see the four functions that this device has, and those are all for the tracer. A second function that it has, as I showed you earlier, is the injector. And it also has an on-off volume control. The injector comes out of the jack up in the upper right-hand side. And of course, the audio comes out of the speaker there if you're using the internal speaker. Finally, if you want to plug in an external speaker, you can do so in the jack at the far upper right. I've plugged in the probe that you see here, and the probe looks like this. And I've connected its ground lead on the radio. And then I'm going to turn on the radio, and now I'm going to put the probe on the top end of the volume control. So you see, you get the audio output. Now let's look at the meter as I do the same thing.
What do you think of that? I don't think too much of it. I understand those guys, I guess, they go out there have fun or do whatever,
So you see that you can get both a visual indication of signal strength as well as an audible indication. Now that's audio. What we can also do is go through the RF stages of this receiver. The AM part is shown at the bottom. On the left, you see the ferrite bar antenna. This is what picks up the signal. The control up here is the tuning control. Basically what that does is adjust the oscillator frequency to produce a difference frequency between the incoming and the IF frequency. These transformers are tuned to a fixed frequency. In the case of this radio, it's about 455 kilohertz. So let's suppose that you're receiving a station at 1455. That is 1 megahertz higher than the IF frequency. That means that the oscillator has to produce a 1 megahertz signal. It mixes with the 1455 signal, and it produces a sum and a difference frequency. The sum frequency, of course, is up near 2 megahertz, and it gets rejected by the IF. The difference frequency passes through these transformers, that is at 455 kilohertz. Each stage contains a transformer and a transistor to amplify the signal. So these are tuned amplifiers, and after it is detected, it's fed to the output. Now, when it's detected, it becomes audio frequency, and the audio frequency is amplified by this little integrated circuit here. So now, let's take the probe. We're going to switch it to the RF position, and we're going to try a few sections in this radio to see what it sounds like as we're tracing the signal.
Get it. I wanted to do it because of the way
what I have done is connected the probe through this test lead to a test point. And I'll show you the test point in a moment. This test point is in the middle of the IF chain. And what is happening is the signal tracer is demodulating that IF signal, amplifying it, and sending it through the speaker. In other words, what we have shown is that from this point forward, the radio is working. Now, of course, this particular radio is working all the way through, but suppose that it was not, and you attach to a test point inside the IF chain. That means that you know that everything ahead of that, that is the tuner and the NEIF stages ahead of that point you're connected to, is working. So what you then can do is move to another point further down the line. Now I've moved it to an earlier test point. You see it right there. And I'll show you those two test points on the schematic in a minute. Because what I want to illustrate is, you listen, I have not changed the volume. You'll notice that there is much lower volume. The specific test points we were working with were TP4, TP5, and TP6. These are the IF transformers, and these, of course, are the transistors that amplify the signal. So what we were essentially doing is checking the output of this stage, the input of this stage, and the output of this stage. Now let's take a look at the signal injector. Here is the output of what is called the injector. Basically, this is simply a signal generator. What I've done is I've hooked the injector through a cable over to the input, and I've put it in the AF position. Now what I'm going to do is I've turned on the injector, but the volume is set to 0. I'm going to slowly raise the volume. And you hear that tone. It's around 1,000 hertz or kilohertz. And the purpose is to use for injecting into the stages of the receiver. I've turned on the injector and turned up the volume on the radio a little bit so we'll be able to hear. The first thing I'm going to do is inject a signal at this point. And what that tells us is that everything from that point to the right is working. Now I'm going to inject a signal starting near the RF section, or actually in the RF section, the input to the IF amplifier. And you notice the volume that we get there. And then what I'm going to do is move to a later stage. And it's a little hard to tell, and that's one of the problems with injecting. The volume seems almost as high as it did earlier. It actually is a little bit lower, but partly because of the AGC action of the receiver, that is the automatic gain control, or sometimes called automatic volume control. The volume seems almost as good at this point as it did earlier, but actually the radio is working harder at this point because to produce the same volume. But nonetheless, what we are showing is that when you know, for example, that a signal injected at this point is coming through, you now know that everything to the right of that is working. So when we injected over here, that basically tested all of the IF section and the audio section. Here is the waveform of the injector signal. The frequency is 984 hertz, so a little under a kilohertz. And it basically is a square wave whose amplitude you can vary with the injector volume control. The point is that it has very fast rise and fall time. That is what generates the harmonics that allow you to use this in an RF section. It generates harmonics out into the hundreds of kilohertz, if not low megahertz range. Now suppose you're working on an FM receiver. I've switched this Elenco kit from AM to FM, and the question is, how useful is the signal tracer and the signal injector in an FM receiver? Well, first let's find out. Obviously, we know that we can look for audio signals, so let's do that first. And I've hooked up the scope here to the output of the signal tracer that's here. And I have the signal tracer right now set in the AF mode, that is audio frequency mode. So let me now touch the test probe while you watch the scope to the audio or the output of the ratio detector. As you see, we're able to do somewhat the same test on the FM receiver that we did on the AM. In other words, we're able to verify that from the detector on, everything in the receiver is working. Well, that's nothing really new. We had actually verified that when we tested the AM section, but what it shows is that you can use a simple signal tracer, in fact just a simple audio amplifier, to do these kinds of tests. So what about in the RF sections? Well, let's see how useful this particular signal tracer is. I've connected the input to the signal generator to this test point, which I'll show you on this schematic in a little while. This is in the middle of the FM IF section. And what I've done is put a signal generator over here, and you notice that the output of the signal generator is just hanging in free space. It's not touching anything in the receiver. So it's just radiating a signal from here into the FM antenna, and then it's being converted to the 10.7 IF. So let's see what we are getting. And as you see, we're getting a usable signal through the IF. And how can that be? Let me turn the volume down. Remember, we've got an FM receiver and an AM generator. This is a leader, LSG-15. It's just a simple AM signal generator. And we're putting out a signal around 90 megahertz, which is about where the receiver is tuned. But we're able to detect that using the RF detection. That is, we have this in the RF position, so we're detecting this, but that's an AM detector. My point is that everything in an FM receiver, from the antenna all the way to the detector, is exactly the same as in an AM receiver. In other words, a superheterodyne is a superheterodyne. You bring in this case, a 90 megahertz signal, mix it with a 100 megahertz or 100.7 megahertz oscillator. That converts it to 10.7 megahertz. You amplify it through an IF chain, and you can detect that signal throughout that IF chain at 10.7 megahertz as an AM signal, as long as you're using an AM signal. Now, if you're trying to receive an FM signal, well then, of course, that makes this less useful, because this doesn't have an FM detector. And in fact, the ratio detector in an FM receiver suppresses the AM component. So if we were try to look at the output using an AM input, we would find that it was greatly suppressed by the circuitry. It's designed to do that. But the whole point I'm making is that except for the FM detector itself, everything in an FM receiver can be tested with this same signal tracer. The only thing that you need, that you didn't need in the AM side, was a source of AM signals at FM frequencies. In other words, you could just tune in an ordinary radio station to get an AM signal on the AM band. But if you tune in any station in the FM band, it's going to be an FM signal, and of course it's not going to be properly detected by an AM detector. But if you use something like an AM signal generator, and it doesn't have to be a fancy one, these are available on eBay for sometimes as little as $5 or $10, and all it has to do is be capable of generating signals high enough in the FM band to put out an FM signal. In this case, it's about 90 megahertz. Now, if you're only interested in looking at the IF section, it only has to put out a signal up to 10.7 megahertz. So even if you have a generator that, say, stops at 50 megahertz, you can still use it for most of the FM, because you can test the IF section by injecting, say, a 10.7 megahertz signal near the output of the mixer, and then following it through using the AM detector. I hope this is useful to you, and I hope that this whole idea of using signal tracers will perhaps reawaken interest in them. They're not really outmoded. They are still useful today, and although the original applications of these was back in the 30s during the heyday, or some people call it the golden age of radio, they're still useful today, and they're still useful in receivers that don't necessarily have AM detectors, as long as you have an AM signal that you can use to trace. The place that we've been testing, that is connected to, is TP9, which you see here is the center tap of the output transformer for the last IF. On the other side is the ratio detector, and we could have chosen any of the test points for any of the IF all the way back to the mixer, and we even could have possibly detected a signal on the output of the RF amplifier. Now, the problem with that is that signal would have been at 90 megahertz. It's before conversion. And at 90 megahertz, the signal tracer and the detector in the signal tracer might have been at least on the edge of working. So you don't always get a good signal through a signal tracer at these very high frequencies like the input frequency of a FM receiver. Because like I say, remember this is operating up to about 108 megahertz. But you certainly can trace the IF strip of an FM receiver all the way through at 10.7 megahertz with virtually any signal tracer, including those that were made back in the 30s, before they even had FM radio. So, once again, remember that we're not testing an FM signal here. We're putting an AM signal in and tracing it through just like it was an AM receiver. The only thing is, we're skipping the detector. So, if we're able to get a signal through the amplifier, that is through the audio amplifier from the detector out, and we're able to get a signal from the antenna all the way up to the detector, then we know that the only thing left is the detector. So we can do a little voltage checking around the ratio detector or the discriminator, in the case depending on the kind of FM receiver, and probably find our trouble there, but at least the signal tracer will have allowed us to isolate a particular stage. Obviously, if we had lost the signal, say, between this point and this point, then we would know that this stage is probably the defective stage. Now, do remember that in receivers like this, there sometimes are feedback loops, like automatic frequency control or automatic gain control. You sometimes may need to disable that in order to get accurate gain measurements throughout these stages. But other than that, it's pretty straightforward. In part, this is an introduction to what I hope to do next, which is to dig out representative set of the old signal tracers that I own and give you a kind of retrospective review of signal tracers of the past. Now, for those of you that have already watched the video I did on the RCA channelist or the Rider channelist, you already know that back in the 30s, there were very complicated versions of signal tracers available with tuned circuits and eye tubes and all kinds of things. They got simpler with time, but that's a story for another day. So I'd like to wrap up at this point. Hope once again you've enjoyed this and that you will look forward to the retrospective review of signal tracers that I hope to do in the near future. In the meantime, have a nice day.